Okay, good afternoon, everyone. Let's get started. It's 12 o'clock noon, and it's Friday again, so TGIF, everyone. How you folks are doing? Good, great, awesome. How was exam this week? I mean, the Comporg exam, or the Comporg test. Tough? Bad? Oh, wow. Not good? Really bad? Not too bad? Okay, that's good to hear. Bad? Better than the last one. Okay. Wow, I didn't expect it to be worse. It wasn't certainly meant that way. Yeah, let's see what the grading brings. But I thought it was just 4 questions, fewer than before. Oh yeah, IEEE 754 question was probably the easiest. Okay, all right. So why was right shift and division on the test when you said it wouldn't be? Did I say division would not be on the test? And it wasn't even the division; it was the right shift. So something that we learned several lectures ago. So I think you might be getting confused about what this question was really asking for. I mean, I assume you referred to the last question with building the ALU. Okay, yeah, and I know the longer MIPS questions are difficult to write, but hopefully you agree that we grade very leniently and we do not penalize for syntax errors and minor mistakes, because it's quite understandable that you are not able to debug your code as if you had an IDE or Qt and SPIM at your disposal. So the factorial is something I think we the concept should be very familiar to you, right? We've um, you know hopefully you have seen this before. Seemed more fair than the last one to me. All right, so I think what I'm reading here is that for some people it was tough, for some people it was not too bad, for some people it was even better than the previous one. So, but yeah, it's an exam, so questions are supposed to be tough. Okay, so it's not like a pop quiz. So, but so far I think we've been pretty generous with grading, and the results are, I mean, the overall class grades are not too bad. They're actually better than I expected. Is the team project going to be posted after the 7th exam or before? I plan to post their project handout at the end of this week, or maybe on Sunday. So anyway, in the next 2 or 3 days. Can you expect grading for this test to take much less time? Unfortunately, no. It's, if anything, it would be the opposite, because we lost one mentor who was helping us a lot with marking, and quite a few of our other mentors are busy with their own with their own commitments. And TAs, they have to grade, as you know, but for mentors, helping with marking is voluntary, so we cannot really force them to mark. And if they are busy with their other things, that are, then we have just the TAs and very few mentors who are able to help, and that of course delays their the grading. So, and things are not getting better. Sorry, people are busy, and we only have three TAs. So who, worst come to worst, it's all going to be handled by just three TAs. So and yeah, so no good news as far as their speed of grading. Is this lecture 18 or 19? I believe this should be lecture 19. I think. I'm pretty certain, but correct me if I'm wrong. Okay, someone already confirmed. All right. Is there a possibility where we can get one exam dropped? Yes, there is a possibility. But let's talk about it a little bit later. I have some thoughts on this. But let's delay this conversation a little bit more. Okay? Does that sound like a reasonable answer? Okay. And so I see our panelists are all here. How's the weather? Chilly, but it looks very sunny. So hopefully we're gonna get a very good day today. Okay. All right. So one thing that, and let me start sharing something before you get all bored. And again, I have to organize my windows as usual. And Q&A and chat. Only 3 panelists today. Isn't there usually 4? I think there's actually 4 or 5, but some people might not have showed up, and that's why we are down to 3. It appears, right? So we have Dallin, we have Brandon, and we have Shankar. All right, so yeah. Well, let's see how many questions we get, and then if we see we are getting lots of questions, and the 3 people we have as panelists today are unable to handle that, then we can add more. Okay. Okay. So someone says that there are 4. Okay. All right. Yes, and a good note on the homework. Someone is asking, like, how hard are we talking? Yeah, please share your experience. Those who have already started, because I think it would be pretty time consuming. But it seems like for you folks, people who started, they're saying it's not too bad. The hidden tasks that they are coming, yeah, this is true. But if you have all the all their operations kind of tested on your local machine, the worst can happen is like you miss some formatting, like a space or a tab or something minor, right? So it shouldn't be that hard to fix that once you see the output from submittee. To Yeah, someone says it took them total about 8 hours. I think it's a pretty good estimate for for an experienced for a student experienced in C and MIPS. I think that's a fair estimate. But if you are struggling with either of those, easily multiply this time estimate. I'd say by a factor of 1.5, if not 2. Okay, but hopefully, it should not take more than 10 hours. That was my initial estimate. Okay, and so one thing I wanted to talk about is actually we released their grades for test for the day before, like very very short time before test 5, so we didn't get a chance to talk about their the solutions, and the solutions were posted. Hopefully you had a chance to review them. And what I was 2 things kind of surprised me. One was that, and let me open their PDF actually of exam 4, just for PDF. All right, so one was that open-ended question. Was it question 3? Yeah, question 3. So amazingly um, it was I thought it would be an easy question, but many and I think most people, pretty much everyone, answered that question, but we have seen a lot of answers that were not correct, that didn't really explain why. They didn't give compelling reasons. So and I don't have like a recipe for how to answer such open-ended questions correctly, except for you just need to kind of have a good understanding of the topic, and then I think that would allow you to answer such questions. And yeah, so it's not something that you can even like prepare yourself for specifically. apart from just knowing the material. So if those questions seem easy for you, just be careful, right? Because it turns out that they can be tricky. And like I said, they were not. This question was definitely not meant to be tricky, but it turned out many people lost points on this. And then as I was thinking about what we discussed last time about. So let me go back to our arithmetic and carry a look ahead, right? So what I think is, is helpful, might help in many situations to kind of visualize the problem easier is some analogies that you can, that kind of relate to you more than you know just electronics and gates and ones and zeros, something more that kind of appeals to you more than those new things that are still a little foreign to you. So things like liquids and pipes and stuff like that. So inspired by, and that is, I think, a very good approach that they use in this textbook. And so we have seen this with the uh, carry look ahead topic, the explanation of the carry look ahead topic, and we will see it at least one more time when we start talking about pipelining next time on Tuesday. Right, there will be another, I think, great analogy that explains pipelining with washing your laundry, and I think that's a very that's a very strong approach. And I, inspired by this, I wanted to comment on this question 6 from our test 4, which again, a little surprisingly to me, was one of the questions with the lower scores. I think it was the average score on question 6 was like 60% or thereabouts, whereas I thought it was a pretty easy question. So, and one student told me that it was like a puzzle. Well, maybe it was like a puzzle, but still, some people were just stumbling and unable to kind of even approach this. So if that happens to you, try this. So yeah, I'm just reading the comments in the chat. All right, so try this. Try thinking about an analogy that would appeal to you. So the analogy I want to offer you is what is your favorite drink? Your favorite beverage? Water, tea, eggnog, Fanta. Okay, water. What do I choose? All right, let's make this soda. All right, so soft beverages. Because it just with eggnog, I don't think that there's like any classification of eggnog. With water, well, maybe you can help me, right? So is there some like is are there any other distinctly different types of water? So like with soft drinks, we get diet and regular. Is there anything like that with water? Oh, sparkling and still. Cool. Right. So suppose we have sparkling and still. This is one classification, and then fruit infused, and what would be the other? Okay, mineral and spring. Okay, so it's another classification, right? Mineral and spring, and we can have 4 combinations, right? So we can have sparkling mineral, sparkling spring, still minerals, still spring. Is that close to how it happens in real life? Okay, cool. So yeah, I only drink water, from my faucet, so it's just one type of water. But we got it. All right. So now let's use some. So let's denote mineral as M, and let me just use a different color. All right, mineral would be M, and spring would be P, and sparkling would be S, and still would be T. All right, and so imagine you have four, types of water that you have a bar, and you're serving, these four types of water, and you need, so you have like, four kegs. So let's label them, and it's gonna be first mineral and sparkling, and then mineral and still, and then it's gonna be spring and sparkling and spring and still. Okay, so you have four barrels, four kegs, and so you need to decide, the hardware to actually, route the water to their tap to the faucet, so that you can serve, the correct the correct type that the customer orders, right? So, and so obviously if you had a four-way switch, that would be a trivial solution. Just, connect four pipes to the inputs, to the input of that switch, and then one output would be connected to the faucet, and you're done. But the limitation here is that you have only two-way switches. So a switch with two inputs and one output. Okay, so and now you have a problem because so imagine we have like four pipes coming out of here, right? And we somehow need to connect them to here, given only two-way switches. So how do you propose we proceed with this analogy? And if you look at my diagram, hopefully it gives you a hint of the way I placed the components. Any thoughts? So you can only select between two things at a time, not four, two things at a time. That diagram is a bit confusing. Why? This is a switch, right? So this is the output, right? So basically, and these are two inputs. So you can either connect this or input to the output, or you connect this input to the output. Okay, so by flipping the switch, you direct either the stream of fluid from this upper pipe into the pipe on the right, or from the lower pipe to the pipe on the right. Their objective is to allow the bartender, to operate these switches to select any of the four beverages that you are offering. So your customer comes in and says, I want to have a glass of mineral still water, and you need to pour them that glass of water. Yeah, exactly. Basically, we are making a four input multiplexer using two input multiplexers. Yes, it is in regard to question 6. Okay, so the idea is, well, if we can only select between two things, we need to have two levels of selection. Okay, and if you look at our classification here, it hopefully gives you a hint. So first you select whether the customer wants sparkling or still, and then of course you have to kind of duplicate the selection for both types of water, mineral and spring. And then once the first selection is done, so I call this like Roman numeral 1, then you do this second level of selection of the type of water, mineral or spring. So to connect this, we have this connected like that. All right, so this is a pipe. All right, so this switch now selects, all right, so it's mineral, definitely, but is it sparkling or still? Okay, so that's the selection. So here we're going to have either mineral and sparkling or mineral and still. And the same selection has to be done here for our spring water. Okay, so this is going to result in this pipe is going to have spring water, either sparkling or PNT, spring and still, okay, because it is a two-way switch. So now, uh, hopefully it's clear how to connect it further. We just connect it like that, so that here the proper sparkling or still has already been selected. This is decision 1, okay, and then only the second decision, this is Roman numeral 2, needs to be made. So do they really want their sparkling or still mineral or spring? Okay, and that's the second selection. Okay, so and here we have our water pouring into the glass. Okay, so I don't know if this analogy is helpful. I think it is, because it kind of appeals to things that you might be more familiar with than with ones and zeros and gates. But the important thing here, so now when you translate it back to their to our multiplexers, you need to think not just about the inputs. We've seen a lot of students, well, a fair number of students who kind of had the idea right, who had and they even labeled I0, I1, I2, I3, and that was looking good. And then they connected it to another 2 multiplexer, and some people of course didn't label anything, but all right, we it was just a minor deduction. You were only allowed to use 2 multiplexers, so that was okay. But some people either left out this selection bit, the selection signal, or they didn't put correct labels on them. Okay, so what would be their selection for the first level of gates? Well, we see that this selects, right, in our analogy, sparkling versus still. So they have, so these 2 valves, all right, these 2 switches, they have to be synchronous, right? We select sparkling or still, right? And we move those 2 switches always, concurrently. We always like they, like they almost have like a hard physical link between them, right? We cannot have them pointing to different things, right? Otherwise, it's not going to work as intended, right? So we move them, to bottom position or up or top position, but synchronously together. That they are hard linked, and that means, all right, because it selects sparkling or still, right? And if it's sparkling, then it should be sparkling for both the mineral and the spring water. And that's why, this is really the same signal, all right? So there's a dot here, right? And yeah, we probably don't need to uh, use indices here, right? So for each individual multiplexer, this would be called S, all right? But for our, and remember, we are building a 4-input multiplexer, a component, right? So those would be, kind of the limits of the component that we are building, right? So it's going to have 2 selection signals, S0, S1, okay? And so we have to kind of do this, and then obviously this one is, is their selector signal for the last multiplexer, and this is the output. Okay, so it was crucial to see that this first one of their selector bits needs to be connected to both their first level multiplexers, and then their second bit of the selector signal would be connected to the selector input of that second level gate. All right, is S0 the first or the second digit in their in the binary signal. So it really, if we write it like that, S1, S0, then of course S0 is assumed to be least significant. 0, 0, 0, 1, 1, 0, 1, 1. So it is usually the convention is like that. Okay. In our case, it doesn't really matter because like if you instead of having this first level selecting between sparkling and still, you could swap them and have this first level of switches selecting mineral versus spring, right? And then you would have their second level of the second level switch selecting between sparkling and still. So it wouldn't make any difference. But if we are talking about numbers and signals, yes, of course it should make a difference between it should be I 0 should be routed to output. So let me put it this way. Uh, Output would be I0 in this case, I1 in this case, I2, and I3, right? Because now we have this correspondence like, oh, this is like number 0, so it should match this index 0. This is like number 1, it should match this number 1 here, so something like that. Okay, so that was just my little speech about trying to find analogies from not electronics or computer science or bits or Boolean algebra to help you with visualizing and conceptualizing all that stuff. Right. So let me move back to where we were, and we stopped here when we were talking about the memory. So we were approaching memory, and that's where I believe we stopped last time. My window's around again. Okay, and so what we found is that this is really a stable element, right? It has a particular state, and even if we remove this signal A, then it appears that the output, this C, maintains the state that it previously had. So, and the reason for that is this feedback, right? This feedback connection that kind of helps this element to support its own output. Okay, so that's why we can say, well, it is a stable a stable state. It's a stable element that we built, and so this is really great because what we really want is we want a bistable element, right? If we are trying to come up with memory, right? We want to be able to set either 0 or 1 as the output at our pleasure, right? So we want to have the freedom of, setting this C to 0 or 1. So we want to have like a bistable element, an element with two stable states, and have the ability to, at our fancy, switching between them. And that's, this feedback idea. Hopefully it hints you, but like I said, it's not a trivial it's not a trivial thing to guess if you don't know it in advance. But in retrospect, you think how you can kind of see how how it makes sense. But to synthesize a bistable element based on just this idea, I think might be a little bit too much to expect. But in any case, here is their idea implemented. Okay, so this is a bistable element, and we can see exactly why it is bistable. So we have, and it requires that we have two gates, and it turns out that we need to actually invert the output of this OR gate, and similarly here, right? And kind of there, an intuitive explanation why we need a second OR gate is because previously we had just a single stable state element. Okay, now we have to have bistable, which means like we have to have two states so that the state is either 0 or 1. Okay, and so we of course need to label those inputs differently, so we call them S and R, and it will become clear why those letters are used. And Q is just the output. And let's see what happens. So let's imagine that we have 1 here and 0 here. Okay, so let's analyze our circuit. So this one means that OR is 1 and negated is 0, right? Yeah, and you can totally see this, do this in open circuits and play with it. And we will do this in a few seconds as well. Okay, so this is 0. So this 0 gets here. Okay, so it's like a feedback, but not back to itself, its own element, but back to it's a feedback, right? A feedback is just a reminder, by definition, is when we route their output back to the input. So not this Q with an overbar, not Q is an output, and when we route it back to the input of this gate, it's a feedback. And so it's 0, and therefore 0 and 0 0 negated is 1. Okay, and so this one obviously is the same as 1 here, it's the same wire. And that's it. We have a stable state, right? So this not Q is 0, Q is 1, and there are no transitions in this circuit. So it is definitely stable. And the reason we call this Q is because it is out. We call it direct output. This not Q we would call inverted output. And we see that they are from this example, we see that they are the opposite of each other. When Q is 1, not Q is 0. And this stat actually stands for set, right? So we see how we were able to set the state of this circuit so that Q is 1. So now what happens when we switch this S from 1 to 0? Okay, so we deassert S. And it turns out that nothing really changes, right? Because this 1 is still here, and the output not Q is 0. So this lower OR is 0 inverted 1. This 1 gets back here. So it maintains the state. So we used S signal to set this circuit, and this circuit is called a latch. And then it just maintains this state even in the absence of active S signal, right? Active in this particular case is 1. Okay, so when it's not active, it's 0. So Q remembers the old value that was set using this S signal. Now let's look what happens when we assert R signal. We switch it to 1. Right, so then, well, now there's going to be some changes, right? Because this OR gate is going to have 1 as their output, inverted is going to be 0, so it's going to switch from 1 to 0, which means that 0 appears here, and it now means that, oh, there are 2 zeros, so, inverted, it's 1 here, and it's 1 here, and the output is 0. But yeah, so it turns out that pretty much this circuit flipped, and another name of a slightly different component will be a flip-flop that we will see shortly. So you see how this R signal, and R stands for reset, right? It makes Q 0, and correspondingly not Q is still correctly matching our Q. If Q is 0, not Q is 1, and we see that we reset it. So Yeah, and someone is saying that yeah, feedback is like a loop. Yes, it is a loop, and that's why it's called a feedback loop. Feedback loop. All right, so that's the idea, and of course all those all this switching has some time delays, okay, which we should be able to see if we do our circuit wise. All right, so let's do this in circuit wise, and it's going to be here. Right. Okay, that was our old circuit, and yeah, let me just make a new. So many tabs. Yeah, I know. I'm glad you haven't seen my Firefox. I think I have like 300. All right, plus one tab. Yeah, because I'm an optimist. I think, oh, I come across something and I know if I just bookmark this page, I'm never gonna get back to it. So I leave it as a tab open, thinking, oh, I will, it will be, in front of my eyes, so I will get to it very soon, and I will look at this interesting material, and I will have time to read it. And of course, it never happens. So just tabs keep piling up, and then when I have a few spare days, like over the break, then I kind of radically reduce the number of of tabs. But then in another semester passes by, and I have 300 tabs again. All right, so all right, and yeah, so let's do this. We need gates. All right, so we need NOR gates, and of course you can build that with other types of gates, but we're not going to be fancy, right? And so we just want to do exactly this, and so what I want is the flag. And we need two flags because we have two outputs, Q and not Q. And let me change the orientation left. Well, actually, let me do this. Orientation is going to be right. So those are going to be inputs. And let's see if I can just do a button. And another button. And then we have our feedback. And then it's going to be F1 and F2 for set and reset. And then finally, I want to have flags. Now this is going to be Q, this is going to be not Q, this is going to be S, and this is going to be R. Okay, and I want to connect. It's not Q here. All right, and so then I need my timing diagram, and I want to auto calibrate, and I want to make it a little larger. All right? And I want to increase delays on, let's do it even 1000 if it accepts it. All right, 1000, 1000, okay. And so now let's see, it is in some state, all right? So Q is 0, not Q is 1, so we're good. And so we switch this button. Open circuit has a timing diagram now, and you still don't use it set. Oh, I didn't know that. As of yesterday, wow. Open Circuits is a fantastic team. All right, I will. Yeah, I'm impressed. Uh, I'll definitely start using it. Wow. Yeah, Leon and his team, you are fantastic, folks. I didn't know. So yeah, I haven't checked my Discord lately. Yeah, I'm pretty certain you told me on Discord. I haven't. I'm not. I'm behind on my messages on Discord. Yeah. All right. Anyway, so next time we go, I'll definitely go back to open circuits then. All right. And so what did I do wrong? Why is it not working the way it is supposed to work? So it's 1 and oh, okay, because it's already set. So yeah, it's yeah, everything is right. So it's already set. So now we want to reset it, and you see how it switches to 0, and I set it again, and I reset it. The only thing I'm not sure is why their timing diagram is not working. So maybe it wants to have a clock. All right, so let's do. Well, let's see if it's just gonna work with a button. Okay, and I switch it to 0, and I switch it to 1. And the delay was supposed to be 1 second. And I see that it switches, so maybe bring it back to. Okay, so now it is working. All right, so you see that S and R are both zeros, and my Q is 1, as it should be. Okay, and now I click on reset, and yeah, you can see that it switched. But let me zoom in. And zoom in and zoom in, so that hopefully, yeah, it's still not showing me their time difference that I wanted, right? So, but the idea is that you see that I can, set multiple times, and of course it doesn't change anything because now my output is at 1, okay? And let me make another attempt yet to adjust the latencies on those gates, and hopefully if the model that they're using is correct, if it's really the model of an electric circuit, not just a logical circuit, then we should see those latencies in the effect of those latencies. All right, so all zeros. Our Q is high, so Q is 1, and then we reset. And now, yes, now you can see there. You can see there. Come on, why is it? All right, now you can see those. Zoom in even further. Right, you see that when I pressed R, okay, that their Q switched first, okay, and that kind of makes sense, right? Because R is connected to this gate, and Q switches first from 1 to 0, and then that change is fed back to their top gate, and that one, not Q, switches from 0 to 1. Okay, so if we look, and let me see if I can zoom in even further, just to make things even clearer. And if I capture this thing with the snapping tool, okay, and I can zoom in here even further, so we clearly see that our changes were due to this switch of R from 0 to 1, right? So it used to be 0, now it's 1, and that change caused, right, this not Q, right? This is not Q, this is Q, and this is R, right? So not Q to switch from 1 to 0, and then this change caused Q to change from 0 to 1. So that's that's the timing of this, from R to not Q to Q. Okay, isn't the one in the bottom Q? Oh yeah, the bottom is, yeah, the bottom is Q. This one is not Q. Thank you. And let me. No, the bottom. Yeah, the bottom is Q. You are correct. And I just need to. No, I don't want to erase everything. Okay, so it should be like that. Thank you for noticing. Yeah, but the analysis is correct. So from R is connected to the gate that produces Q. So yes, this one switches first, and this switch causes not Q to switch. Okay, so and that's the idea, and we see how this whole thing works. All right, so now back to our slides. Of course, those of you who are curious might ask, well, we see that when both S and R are zeros, nothing happens. This circuit just maintains its previous state. When S is 1 and R is 0, we set Q to 1 and not Q to 0 correspondingly. When R is 1 and S is 0, we reset the circuit. So we set Q to 0 and not Q to 1. And of course, we are curious what happens if we have S and R both at 1. You have any thoughts? What would happen if I put S and R both to the state of 1? No MIPS on the next exam? I don't know. It's too early to say. But we are largely done with MIPS. So even if MIPS is present, it's going to be not a whole lot. All right. Anyways, so back to our gates. Yes, exactly. So it and we can try it. All right. So we set this to 1 and this to 1, and we see that interesting. Someone was saying that both Q and not Q would be 1. But what we see is the opposite. Q and not Q are 0. So it basically means that uh, they're what we're going to see is that Q and not Q are going to be the same. And it's clearly not right? Because we designed the circuit with the idea that Q is the opposite of not Q. They should be, in inverted versions of each other. They should not be the same. And it also means that we don't really know whether our Q and not Q are going to be 0 or 1. So it's not deterministic. The answer is really it depends, right? So that is exactly what is happening with this circuit, right? So this is the SR latch truth table. So this circuit is called the latch because it can, it can latch or hold the value. And when S and R are both 1, then their output is not deterministic. It means it's going to be, of course, something specific. It's going to be either 0 or 1. So when you read this uh, with this phrase that says undefined, let me switch to red, right, is undefined, it doesn't mean that it's going to be something different from 0, 1. It's going to be 0, 1. There's no other way around it. But it means that you don't know whether it's going to be 0 or 1. And worse, you know that it's going to be the same value for both Q and not Q. And this is, completely contrary to our design. And the truth table here, note how it now has the notion of time. So this t here is discrete, discrete time. So qt is current state and qt plus 1 is next state, the state of this output q at the next time step. Again, here we assume that time is discrete. And yeah, so these combinations here are, are non-deterministic, and that's bad. We don't want anything to be, yeah, glitches in the matrix. Exactly, we don't want anything non-deterministic in our digital circuits, right? Because it just adds uncertainty. How can we use this component if we don't know in certain mode whether its output is going to be 0 or 1? Okay, so what do we do? How do we solve this? And this is something that you should be able to guess if you think, right? So their problem boils down to the fact that we have two signals, S and R, and therefore we have four possible combinations of those signals, and we want to kind of get rid of one of those combinations so that it never happens. Exactly. Don't allow both S and R to be 1. And the way to do it is just throw in another gate or maybe several gates to ensure that even if we have SR as external signals, right, then S and R that are outputs are guaranteed to never have 1 and 1. And of course, you need to decide what so this is S, this is R, this is S prime, this is R prime. What to do if you know their input is 1 and 1? So obviously, for all other combinations, their outputs are obvious. And what to do for this fourth combination? Well, you can say, well, I just want to keep the previous state, for example. All right, so I just want to output 0 0 if my input is 1 and 1. Okay, because it's not going to change anything, just basically keep the stored value. All right, and then you can design this using all the methods that we discussed. All right, and this is the timing. So we'll get back to what happens when we fix this problem with an S&R gate, but here I think we pretty much saw this in the simulation. So here we have the S. Note how this is their latency. Why is it 2 delta t? This is important because we see that from S, uh, their first change is going to be in this gate, and this is delta t, and then through this feedback wire it's gonna be in this gate, and it is another delta t. So in that sense, their path is that our changes are going through will be as follows. From this S, right, the change will propagate to the output, and then to the input of this gate, and then to its output. All right, and that's it. Okay, so and therefore it's like a serial connection of two gates, because when do we know, how do we know that our all the transient processes, all the switching in our circuit are done? We know it when both Q and not Q, when our outputs have received their state that corresponds to the inputs, and there will be no further changes. So obviously, for this to happen, the changes have to go through both gates, and through both gates sequentially, right? Because it's kind of, due to this feedback loop, it's one gate that then sends its output to the input of the other gate. And that's why there's 2 delta t, and it's going to happen on on any switching, right? So 2 delta t here as well. Whereas of course, if for S to not Q, it's just one gate, right? Delta t. So and obviously from R to here it's delta t. So Q reacts to the state of not Q. Well, Q reacts to both, right? So we see that it has, it depends. If you look just purely at Q, let me switch colors so that I'm not making the mess, right? So if you look at Q, it depends on both R, right, through this gate directly, and actually it depends on not Q, which in turn depends on S just through the longer dependency through another gate. So you cannot say that Q is just a function of R and it doesn't depend on S. Okay, so it's more complicated than this, right? But we see that if R changes, then Q will be changed first, and that's something that we have seen, right? So this is exactly what I showed before on the real simulation, right? From change of R, first we have the change of Q, and then from that change of Q we have a change in not Q, and each latency is delta t, so the total latency for this whole circuit is going to be 2 delta t's. All right, and so we another thing that is that another observation that we can make is that this circuit, it is sensitive to S and R, obviously. All right, so it might change its outputs depending on S and R, but it's sensitive to the level of S and R, not to the edge. So it's important that we have this S here, okay, and it has to have a certain duration, and that actually presents a significant problem in designing real circuits. So again, let me see what so it's a delay of 500, and let me reset our timing diagram and calibrate it. Right, so and yeah, so let me switch it to this, and again reset. All right, and so now we switch it, and I'm not sure why it is. All right, so, and you see that, oh, I'm flipping this input so quickly that, given the significant delay that I set for my gate, it's just not enough to trigger the changes, right? Hold on. No, it's 1. So it's let me try this actually with a reset. No, I wasn't quick enough. It's still triggered. Okay. Well, what we can do is we could use a clock. Where is the clock? Come on. All right, here it is. So let's do the clock. And let's program the clock. Okay, so the clock is going to have their frequency of their main clock time simulation. So let's make it 2 seconds. Okay, and we see that, all right, so we have a queue of 1, all right, it's set, and if I click reset when S is 0, so let me wait. Let me reset it, and 0. Right, and look at the output. You see that when I click the button to reset, so Q went to 0, okay? And then we had a short period of, this forbidden state, 1 and 1, this, then, everything went back to normal, okay? So now let's see what happens if I have a very short clock cycle. Let's make it 20. So you see what's happening? So despite the fact that S clearly goes to 1, right? And it goes, 0, 1, 0, 1 very quickly, and we can see it. Okay. There is no and okay, it's set. So let me reset it. All right. So what I'm trying to show here is that if the duration of their pulse that is supposed to set or reset is shorter than their delay of one, individual gate, then this effect is not going to be observed. Okay, and their circuit will not switch just because it has to, the duration of this one pulse of set should be long enough that this one propagates to the output. If it's shorter than that, it's not going to happen. And this is a big problem with such circuits that need a certain length of the pulse to make sure that they work. And those circuits those bistable elements that switch on a certain level of their input signal are called latches. Okay, and so how do we fix this problem? What we actually want is to make sure that this circuit switch not on, just this one signal being present long enough, but on the rising edge, and we show it with an arrow. Right? Every time there is a change, we want our circuit to kind of react to that change, and this change is very short. Right? So it doesn't matter if so basically what we want is our switch to happen on this rising edge, and then even if very shortly this S signal goes down, the switch would still be made. So there is no we want to avoid the dependency on the length of this pulse of this state when S is 1. Okay, because we want changes to happen on the rising edge, and the way to do it is to introduce the clock. Right? So, and that's how we get to the clocked SR latch, and the latch that is clocked is called a flip-flop. So we want gates to change only at specific times, and that requires additional circuitry. Another analogy from like a real world is, imagine you have in your elementary or middle school, the class goes to lunch, okay, and in in a non-clocked fashion, non-synchronous fashion, also called asynchronous fashion, every student, as soon as they're done with their lunch, they are free to return to their classroom. And of course, they're not going to return all at the same time, right? Because they all are going to finish at different times. And so students who return to the class earlier, they may start, working on their problems in the class. They can do whatever, they can fool around. So there's really no way to ensure that everyone gets their same amount of time in the classroom, because they're going to return at different times. And compare it with a clocked fashion, right? So if we have a teacher who is at their entrance, at their exit from the cafeteria, and then not letting any individual student out of the cafeteria until the entire class is ready. Okay, and also imagine that it can only happen at discrete moments of time. So it's not like the entire class is ready and they can leave, right? Let's say the evaluation is done every 10 minutes. Okay, so at time zero, at time moment 0, their teacher checks if their class is ready or not. If even one student is not ready, the entire class stays in the cafeteria. Next time moment 10 minutes, it checks this again. Is the entire class ready? Even if one student is not ready, the entire class stays for another 10 minutes. Okay, and only when all their students are done with their lunch, and it's their nearest 10-minute check, that check will discover that all students are ready, and they will be allowed to leave the cafeteria and go back to their class. So this is exactly what clocking does. It's discipline. And in terms of both organizing the school and organizing the circuits, discipline makes it actually easier for you to design things, because there's more, there's less, yes, there's less freedom, but there's also less havoc. There's more, things are more deterministic. So for instance, that all students will return to their classroom together as a group, not one by one, and it can only happen at 0, 10, 20, 30, 40 minutes, but not in between. So the speed of a circuit is determined by the slowest component in that circuit. In synchronized circuits, yes. And from the standpoint of pure performance, it may not be the best solution, because imagine, again, having, going back to this analogy with a class of students eating their lunch, one student is particularly slow. So it might have, you might think it is beneficial to just leave that person behind and just let the rest of the class go back to their studies in the classroom. It would probably be more efficient, but then, from the standpoint of control of, getting things organized, like it's going to be it's going to be a nightmare, because then, oh, what are you going to do with that one student? So you have to send another teacher to get them out of their cafeteria and back into the classroom, or like it becomes a huge problem. So it is actually easier um, to design circuits where everyone is treated uniformly. So yes, even if one person is not done, even if one signal is not yet ready, or one bit of data is not yet ready, we cannot proceed. We have to wait for the slowest component. Yeah, ditch the slower skid. That's the asynchronous approach. But the synchronous approach says, no, we are only as good as the slowest team member, and we wait for everyone to be done. All right, so the clocked SR latch is implemented just using 2 additional gates, and with adding the clock, it is actually becoming what is known as an SR flip-flop. And if you think at this circuit, it's pretty straightforward what it does. So the addition of those AND gates blocks the propagation of S and R signals if clock is 0. So if clock is 0, oops, if clock is 0, then this is 0, this is 0, and then this is our SR latch that we have seen before, right? And it's not going to change its state when both S and R inputs are zeros. Okay, so even if this is 1, this is 0, or whatever, right, this one will not go through this AND gate because it will be blocked by the clock, which is 0. So when our clock changes from 0 to 1, all right, then at this moment of time, the corresponding edge will be formed on the output of the AND gate. And S and R being 1, both being 1, is still a problem here. So we will fix it shortly. But this shows that there is a clocked thing, and we will now the switching will begin with this rising edge of clock. Okay, and if clock is 0, so we're just not changing anything. All right, and so that we already discussed, right? So the problem is with S and R both being 1. So the circuit is not stable because it can be in state where both outputs are 0 or both outputs are 1. It's non-deterministic. It's not good. And we already talked about the way to fix it. So we kind of combine S and R together, and we can still use the clock. And this design is known as D flip-flop. Okay. So what D does is, instead of having S and R independent, you can almost think of this D as data. Okay. So it's this is your S before, this is your R before, and you know that S and R cannot be the same. So they are either one of them is 0, or so one of them is 0, another one is 1, or the other way around. They cannot be both 1. It actually means that they both cannot be 0 as well, right, in this design, but that's that's not too bad, because we can always say, well, when D is 1, we want our circuit to set 1, and if we still want to set 1, we just keep this 1 here. So basically this D flip-flop will remember the state of D that it had at the time of the rising clock. Okay, so if we had 0 and 1 here, so if we had a rising edge of the clock and D was 1, so we can easily see what's going to happen. So it's going to be a rising edge here, and so this input becomes 1, and then of course this is 0, this is 0, and so we see that this is 1, right? Because this is 1 and this is 0, so this is 0, and this is 1, and this one gets here, and it keeps supporting the output. Okay, and as long as this D stays at 1, even if our clock then goes to 0. So if we have a falling edge from 1 to 0, all right, so we have 0 here, and we have 0 here instead of 1, and we have 0 instead of 1 here, right? But that just means that our circuit maintains its state, right? Because clock is low, clock is at 0. And then when next a rising edge of clock comes, it will again just store this 1 in this flip-flop again, and so on. And if by the time next clock arrives, next rising edge of the clock arrives, this D switches to 0, then this rising edge of clock will make the switch to 0, like that. All right, so this is the D flip-flop. We only have one input, data, and we just discussed how it works, right? So it basically remembers their state at that input. And this is the timing of the flip-flop. For the sake of time, I'm not going to do their simulation, but we can see that, well, this D now doesn't really affect anything while clock is 0. So, D is 1, but nothing is happening until we see this rising edge of clock. And this rising edge of clock, together with a high level or one level of D, they will cause this change. Okay, so now the change happens after we get the rising edge of the clock, not when D switches from 0 to 1, right? Not from the level of D itself or by itself. And when clock goes down, all right, when clock is deserted at the falling edge of clock, nothing happens. Our flip-flop, our D flip-flop maintains its state, Q is 1. And then when D goes from 1 to 0 again, nothing happens until the next rising edge of the clock. And so this rising edge of the clock will cause Q to go from 1 to 0. Okay, and this difference here and here, this time difference, this time delay is our new delta, T, right? So there is a delay. Of course, this delta T is going to be, different. It's not going to be just one gate or two gate delays as before, because now we have more gates. So imagine that, this is one delay, and typically we can ignore this. So in many cases, we can say that we may assume that the delay of an inverter is just 0, but still we have this gate, and then we have this gate, and then we have this gate. All right, so at least it's going to be 3 delays of their gate. If we assume that the delay of all the gates is the same, it's going to be, so if this is delta T, then it's going to be 3 delta T here, okay, until both outputs are completely set correctly. So in the worst case, it's going to be 3 delta T here. All right, and here's the first pop quiz. Let me open it on Submittee. And accepting answers. So it relates to what we just talked about. All right, and then you can use flip-flops. So basically, flip-flop is like a 1-bit memory, and you can have 8 such flip-flops to create an 8-bit memory, right? So that would be one byte of memory, and so basically, you have to operate this memory, you need to have 8 inputs that you want to store, and you want them to all be written at the same time. So you have to use the clock, right? It's our middle school cafeteria or elementary school cafeteria analogy. We want all 8 inputs to be sampled to be read at the same time. So we want all our 8 flip-flops to work using the same clock, right? So that they kind of store the values at the same moment of time. And then we can use this 8-bit memory as a register. So if you think about your favorite MIPS, then the registers that we had 32-bit registers are really nothing but, those collections of flip-flops that work together as a single thing, so that they use the same clock, right? And they kind of operate together. It's just not 8 but 32 bits, right? A little bit longer, but conceptually exactly the same. And here is their their circuit that you can use to build this 8-bit or 1 byte register using 8 flip-flops, D flip-flops, right? Note how the clock is fed, the same clock signal, right? So all those flip-flops are synchronized with each other by using this external clock. All right, so and that kind of ensures that the outputs are also kind of in sync, right? So that the outputs appear roughly at the same time, and that's why those outputs can then be obviously connected to some other parts of their circuit. So if you have synchronization, if you use clocks, as we discussed before, it allows you to actually have your circuit work to get have multiple components of your circuit work together in harmony, as opposed to trying to figure out when each signal is going to be ready and what delays of individual gates are. All right, and that's pretty much it for this part. There are couple additional examples that I wanted to show you briefly before we switch to the new topic. So let me get out of here. And I need to go back to my circuit wise for now. Oh, circuit verse, sorry. All right, so, and I actually want you to do some work, so I'm gonna be asking you questions, and hopefully you can. Why can't we just connect D and the clock with AND and gate it? So you mean here in this diagram? Yeah, we need clock to be supplied, the same clock to be supplied to all flip-flops, okay? So that they all work together, okay? And this is the design of an individual flip-flop. And yeah, there's actually a lot more exciting stuff about flip-flop. I could talk about that, for 2 more hours easily with more examples. It turns out there are other types of flip-flops. There's a very common JK flip-flop, and then there are also flip-flops that used to be called master-slave flip-flops. Now a more traditional a more accepted terminology is like main and dependent, or primary and secondary flip-flops. So it's like 2 flip-flops working together as a pair. So there's a lot more to that, but yeah, let's move on. And so what I wanted to ask you to do is to help me design. Let me see. Let me design a counter. Okay. So what I want from this counter is to be able to count. So imagine I have a clock. So let me pull up the clock. Right, and if we look at the clock, well, it's just the clock. What would you expect, right? So it's just this. So I want a circuit that would count how many pulses I have, right? So every pulse, every rising edge, the output of that circuit should increment by 1. That would be the counter, right? Any thoughts? How do I approach it? Is it going to be a combinational circuit or a sequential circuit? That's the first question. it's going to be sequential, right? Because we're going to need memory. All right, so then you need an adder for this. No, because an adder, remember, it's a combinational circuit. An adder is just there is you know, adds the inputs. And we need some memory thing because we need to remember the previous state, right? Because we are adding one to the previous state. The adder doesn't have memory. We need to have a counter, then every time the clock turns on, we feed the updated count into the memory. Right, yeah, that's basically correct. Any other thoughts? But how do you get the updated count? That's a good question. Flip-flop for each bit, exactly, all right? That's a very promising idea. So let me actually grab this part, and hopefully I'm able to copy, and bring it here. All right, so first let's do the D flip-flop, and for that we can just go back to our design. So we just need two AND gates and an inverter, and okay, and two AND gates. Okay, and so we have a clock fed to the AND gates, and we have some input D. Okay, which we don't know yet what to connect to, but let's for now connect it with some input, and then connect it like that. All right, and so we then have this, and then feedback, then the feedback in the other direction, and then this, and then we just need another flag, the output, and I want to actually connect it to this output. All right, so as you can see, this is not doing anything because this is 0. What happens when this is 1? Okay, it just sets it to 1, and that's it. All right. Any thoughts on what we can do to make this a simple single bit counter? So far, it doesn't look like it really counts. Connect the clock to D. All right, let's do that. Is it doing me any good? Did you need more digits? Well, I want to start with just one. It already counts from 0 to 1, so now it cannot go up anymore. Exactly. It actually does count correctly. All right. So, yeah, we didn't have to, this connecting the clock doesn't really do us any good, right? So it was actually a counter, right? We were not resetting it, right? But it was a counter that counted from 0 to 1, and it's a 1 bit, so we're done. Okay, but you can do the counter with a flip-flop. So let me now take the flip-flop that is, that is like that. It's just, a circuit made internally made out of the components that we had here before, right? But just to make things easier, we connect the clock, and then let me move this stuff here into this. All right, and so then we are going to need the output. So let's just build, let's say 3 bits. No, this is not a connection that, oops, it's not the connection that I wanted. All right, and we need one more. All right, so, and now, so if you want a counter with more than 1 bit, you would connect it like how you connect ALUs in a ripple like pattern. Exactly. I like how you put it. It's a very good observation. Right. So let me also disconnect this and grab us. Well, we're not gonna. Yeah, I'm not gonna be using F2. I'm gonna be using their hex display for this. So it's a display. So it's it's capable of displaying from 0 to F, and so it's 4 bits, so more than we need. We currently have 3. And the only thing that I will have to do with this, right? So this connection is, you see, a single point of connection. So it's essentially a bus, and we need to have a component that allows us to deal with a bus, and it's this splitter component. So we are going to need 4-bit width, and then specify how it is split, 1, 1, 1, and 1. And I put it here, and I just want to switch it to a different direction. And now I can connect it here as a bus, and then those would be the outputs, the bits that I will be displaying. All right, so let me move things, space out our D flip-flops a little. All right, so then what we are going to have is this is going to be our bit number 0, right? So this is just the output, and this is going to be our bit 1, and this is going to be our bit number 2, right? And so now this output here is going to be sent back to their input. Okay, so this is their D input, and their clock will be coming from their output of their previous bit. Okay, so that's that, and yeah, I think that's all I need. So I just need to repeat this. So my D comes from, ID comes from the output, from the lower one, from the negated one. And my clock comes from this one. All right, and so I also need connect this like that. All right, and it is supposed to count. Why am I? All right, yeah, so I need to connect all wires. So I'm just gonna put a constant 0 here. And here we go. 7, 0, 1, 2, 3, 4, 5, 6, 7, 0. All right, so it is a counter, right? We are counting, exactly. So, and yeah, when it overflows, it goes back to 0. And the amazing thing is, if we put if we look at the timing diagram left, and so let's make it this, and then I will make another one and connect it to this, and then I will make another one and connect it to this, and I will so let me rename them F2, 3, 4. Okay, what happened to my diagram? Now let me go back to the slower speed, and so clock is enabled. Yeah, thank you. Yes, I meant not F. I mean this short bit. All right, but what? Why? All right, here we go. All right, so and here's an interesting observation. So you see how the frequency f of f2 is half the frequency of f1, and the frequency of f3 is half that of f2 and the quarter of f1, and the 4 is again by a factor of 2. So basically it is by using one D flip-flop, we can do a frequency divider by 2. Okay, and then divide by 2, by 2, and by 2. So 3 times by 2. So we have a frequency divider by 8. So our most significant bit changes. So our period of our counter, right? If we look at the circuit as a whole, is going to be just 8 times the clock, the frequency of our initial clock. Okay, is it making sense how this works? Isn't that, yeah, isn't that cool? Isn't that crazy? Right? We have a circuit based out of all the components that we just discussed, right? Gates and flip-flops, right? That can actually count. All right, and one more thing. So I know we are running out of time, but I cannot resist. I cannot resist the temptation to show you one more thing, and give you one more puzzle, if you don't mind. Because actually, someone asked me previously, like, all right, how do we do their shifter, right? So this shift left, shift right instruction. How do we actually do that? any thoughts? And we can actually do that with just multiplexers, believe it or not. All right, so let me show you the circuit. So the idea is that for the shifter, so let's do a shifter with just 4 inputs. So let me grab my 4 inputs. Right. So and let's call it A0, A0, and then I'm gonna right. This is gonna be A1, 1, A2, A3. So it's a 4-bit number. And then by how many positions at most does it make sense to shift it? So it's 4 bits. So it's a 4-bit number. How many positions do I need to shift it by? Yeah. So 4 at most, but for the sake of time, let's do just by 2 positions, and then you will see that you can just well 4 positions, right, uh, is requires 2 bits to code. So we can use we could have used 4 individual bits and then have an encoder, but we can actually design our circuit so that we don't need an encoder if we assume that the amount of shift is given as a number. So for example, what our where's my text? So for example, A can be something like 1011. Okay, so that's the number we are shifting, and then S can be like 1 by 3 positions. Okay, by 4 positions, right? So by 3 positions, right? Because if we shift by 4 positions, the result is going to be 0. So really, the interesting shifts are 0, no shift, 1, 2, and 3, right? If we shift 4 positions, it becomes 0. Okay, so that's the meaning of our S, and then all we have to do is have a bunch of 2 multiplexers, right? Hopefully by now you love multiplexers, and here we are going to need 8 of them. Come on, 1, 2, 3, 4, and 4 more. And you will see that actually, the number of levels corresponds to the number of bits in S. So we have 2 bits in S. That's why we have 2 levels or 2 layers. And then we need an output. Let's do hex display again. And we're going to need the splitter, 4 bits and 1, 1, 1, and 1. And we need to flip their direction. All right, and then the outputs are connected like that. Okay, and so now we need to do all the connections, and as I'm making the connections, hopefully you get the idea of why this idea works. So when we shift, okay, it means that the multiplexer selects either between this bit or the bit from the neighbor. Okay, that's why we can actually implement it with multiplexers. So all our multiplexers will be doing exactly this, right? We are selecting between this and the multiplexer, and A3 is connected to here, and then A3 is also connected here. And then, well, what do we connect to this multiplexer? You're getting this? Cool, yeah. So what do we need to connect here? When we are shifting, right? That's going to be the bit that is vacant that we are trying to fill. We're just going to need a constant 0, right? Because that's exactly. All right, and so then this one goes here, and then this one goes here, and here, if I'm correct, and this one goes here, and this one goes here, and then it also goes here. And this 0 goes here. It also goes here. All right, so finally we have to connect S's. So S0 gets here. Let me get S0 gets here. S0 gets here. S0 gets here. And S1, somewhat predictably, is just connecting to all this. All right, let's see what we've got. So we have 0, no shifting, right? So if we have 1, we have 2, we have 3, we have 4, 5, 7. Well, I skipped 6, but you got the idea, right? So no shifting. What about if, and of course we can have 9 and so forth. All right, so what if I have this? All right, so all of a sudden we have 4. Why? Because we are shifting which direction? Yeah, it works. We are shifting right. We are effectively dividing by 2. Okay, but not just by 2. If we only had to divide by 2, that would be simple, right? We are shifting right, so divide, well, by the power of 2, because, well, if I want to divide by 4, here I am. 9 divided by 4 is 2. Integer divide, of course, right? No floating point here. Okay, what if I divide 9 by 3? Well, it's 1. Okay, so it is, we can divide this number by any power of 2. Right? Let's try another something like A. It is 10, right? So divided by 2 is 5. Divided by 4 is 2. Divided by 3, it is 1. Isn't that cool? And yeah, note that it is purely combinational circuit, so there is no memory required for this. This is literally magic, I agree. So if you are wondering how, when you write SRL in your MIPS code, how it actually might have been implemented. That's how, just hardware, just gates, and you learn pretty much everything that you need to build such circuits. Okay, and yeah, so with this, let me actually wrap up. So we didn't start the new topic, but it's okay. We will get to it. We finished, I think, a very important part that will help you, understand a lot about our next topic when we delve into the design of the processor, right? But as far as our next exam is concerned, clearly sequential circuits, memory, and flip-flops, and all the stuff that you can do with flip-flops. Something as cool as this counter. Clearly, you can expect to show up on the exam. So just be ready. All right. So it is magic. So now hopefully you're starting to get the glimpse of like how do computers really compute? Well, that's how, right? That's the link between the program and how the processor really computes the result. All right. So let me stop here. We are at 150. Thank you everyone for attended this lecture, lecture 19. So just not that many lectures left, and it's Friday, so enjoy your weekend and enjoy the sunny yet cold weather in Troy here. All right, have a great afternoon, folks, and talk to you on Tuesday.